Welcome back to Hands-on FPGA Design, from theory to implementation. I'm Albert. Today, in our first lab, we'll start with the fundamentals of Vivado to implement our first hardware control project on the ZedBoard. As this is our first lesson, we'll be using Vivado to program the FPGA. If you haven't watched the pre-lab session yet, please make sure to go through it and have all your files ready. Here is the outline for today's session. Before we dive in, let's verify your hardware. We'll be using the Xilinx ZedBoard. I recommend using Vivado 2020.2 to ensure interface consistency. Also, make sure you have your power supply and 2 micro USB cables ready. The goal of this lab is to familiarize you with the Vivado toolset and practice GPIO control. GPIO stands for General Purpose Input-Output. Simply put, these are multifunctional pins on the chip. By writing code, you can define whether these pins act as inputs or outputs. Let's look at the target functionality. When you press the left button, BTNL, all LEDs turn on simultaneously. Conversely, pressing the right button, BTNR, turns them all off. Additionally, toggling the switches will control their corresponding LEDs. First, let's look at the logic architecture diagram. This defines the hardware behavior we need to implement inside the FPGA. The central block is our core module, the LED controller. On the left, we have 3 sets of input signals. Tie high corresponds to the BTNL button. It's a force-enable signal with the highest priority. When pressed, all LEDs light up. Similarly, tie low forces all LEDs to turn off. The switch signal is an 8-bit input representing the 8 switches on the board. You might wonder why it's labeled SW7 to 0. In Verilog, we follow the convention where the rightmost bit is the least significant bit, or bit 0. So, even though the leftmost switch is the 8th one, it's indexed as bit 7. This notation effectively declares all 8 switches at once. Finally, on the right, we see the LED output. These signals will be mapped to the physical LEDs on the board via our constraint file. Here's the lab workflow. First, we'll write the Verilog code, run a simulation, define the constraints, execute the implementation process, and finally, generate a bit stream to program the board. We'll go through these steps in detail shortly. Before we code, let's briefly compare C and Verilog. C is a software programming language executed sequentially on a CPU. Verilog, however, is a hardware description language, HDL, that operates in parallel, which is essential for FPGA architecture. Also, you'll hear the term RTL, or Register Transfer Level. This refers to the level of abstraction used to describe how data flows and transforms between registers in our circuit. You can download the code examples for Lab 1 via the link below. Now, let's start the project. Open Vivado and click Create Project. Name it Lab1_example and save it in your examples folder. Select RTL project and choose Do Not Specify Sources. Next, click on the Boards tab, search for Z, and make sure to select the ZedBoard. Once in the main workspace, go to the Project Manager, click Add Sources, and select Add or Create Design Sources. Click Create File. Name a demo. And you'll see it's a Verilog file. Hit Finish. Then OK and Yes. You can now see the demo file under Design Sources. This is where we'll implement the LED controller. Let's paste the demo code. Let's break down the code. The module demo declaration is similar to a function in C. The ports defined in the parentheses represent the chip's pins, matching our diagram. Next, we define the port directions and properties. Tie high and tie low are 1-bit inputs. SW7 to 0 is an 8-bit input. For LED 7 to 0, notice the REG keyword. This is required for any output assigned within an always block. The begin, end keywords are like curly braces in C. The if-else logic here defines the hardware priority. If tie high is asserted, left button pressed, we assign FF to the LEDs, turning them all on. If tie low is asserted, right button, we assign 00, turning them off. The else block ensures that if neither button is pressed, the LEDs simply reflect the state of the switches. Next, let's add a simulation source. Create a file named tb_demo. TB stands for test bench. Think of it as a test fixture for verifying our design. Paste the code into the file under Simulation Sources. Now, for the test bench logic, we initialize our environment by setting all inputs to 0. The hashtag 10 indicates a 10 nanosecond delay. We then simulate the button presses, first setting tie high to 1 to check if LEDs turn on, then tie low to 1 to check if they turn off. Finally, we use a for loop to generate 10 iterations of random values for the switches, simulating real-world usage to ensure our circuit responds correctly to all combinations. Now, let's run the simulation and observe the waveforms to verify the logic. From 0 to 10 nanoseconds, all inputs are 0, and the LED output is 0. From 10 to 20 nanoseconds, tie high goes high, and the LEDs instantly switch to FF. From 20 to 30 nanoseconds, tie high drops to 0, but tie low rises, so the LEDs go to 00. After 40 nanoseconds, you'll see the switch signal toggling, and the LED waveform should perfectly match the switch states. Next, we need to create our constraints file, or XDC. This is a critical step because we have to tell Vivado which physical pins on the ZedBoard correspond to our LED variables. Click Create File again, enter Demo as the file name. Once completed, you can locate the file you just created under Constraints within the Sources window. Now, paste your code into the file. By referring to the manual, we can determine the correct pin assignments. Next, we need to synthesize the design with the constraints. In the left-hand menu, locate Synthesis and select Run Synthesis. Finally, to generate the bitstream file for programming the ZedBoard, go to the left-hand menu under Program and Debug and select Generate Bitstream. Once finished, click the second option, Open Hardware Manager, which will navigate to a new interface to prepare for the connection to the ZedBoard. After entering the Hardware Manager interface, confirm that the ZedBoard is powered on, then click Open Target and select Auto Connect. Once the connection to the ZedBoard is successful, simply click Program Device at the top to complete the final step. Once the device is programmed, a blue LED will light up on the ZedBoard. Now, you can use the switches and buttons to control the LEDs. The results are shown in the video. For our next course, we'll explore how to use Vivado's built-in IP cores to build an LED counter with adjustable speed and reset functionality. I'm Albert, thanks for watching, and I'll see you in the next lesson.